In this lesson, I want to talk about the graphs in section A of the physics paper. In particular, I want to talk about the trickier graphs, the ones that cost people marks normally. And the first of these is the graph on the concave mirror or the convex lens. It's a similar graph in both experiments. And what I want to do is explain just the basic maths behind it, which you don't have to know for the exam, but it's nice to know the maths just so you understand why the graph is the way it is. So that's the approach I'm going to use for all these experiments. So first of all, the equation for this graph is 1 over u plus 1 over v equals 1 over f. And let's rearrange that equation by bringing the 1 over u across as a minus. So now you've 1 over v is minus 1 over u plus 1 over f. And just to separate that minus, that's a minus 1 times 1 over u. So take the minus 1 out. And now I'm going to shade in 1 over v and 1 over u for a reason, because the u and v are variables. Therefore, 1 over v and 1 over u are also variable. So they are the two variables. This is the independent variable. You change u and v changes as a result. So if you compare this with the standard formula for a straight line, y equals mx plus c, you'll notice that the x for the x-axis corresponds to 1 over u in this formula. And the same here, the y corresponds to 1 over v in this formula. And that's the reason why the graph is 1 over u along the x-axis versus 1 over v on the x-axis. So you have to remember that, and people have lost marks in the past for just plotting simply u versus v and paying no attention to what's going on in the maths over here. So you have to do that properly. Also, if you understand the equation of a straight line, you'll note that the plus c part stands for where it cuts the y-axis. So this point c here, so this is c, and c corresponds to 1 over f in the formula that we have. So obviously, then 1 over f is c. And this is the whole point of the experiment, of course, to find the value for f, the focal length. So c actually corresponds to 1 over f according to our formula. So that's your next stop up here. Put c equals to 1 over f. Or if you change it around, f is now 1 over c. So you measure c on the graph here. You measure this point here, whatever the reading is on the y-axis or the 1 over v-axis. And that c, you put it into this formula. And finally, on your calculator, you can work it out now. F is 1 over c. So that's how you calculate focal length from that graph in either the convex mirror or the convex lens experiment question. Now on to the second graph that we need to talk about, Snell's law. Again, we look at the maths first to understand why the axes are the way they are. So the formula for Snell's law, refractive index is sine I over sine R. Multiply both sides by sine R, multiply over here, and you get n sine R is sine I. And now shade in the sine I and sine R, again, the variables in the question. So sine I is now the independent variable, and sine R depends on that. Now, if you correspond that to y equals mx plus c, you'll see that x now corresponds to sine R and y corresponds to sine I. So along the x-axis, that's the reason why the x-axis for this experiment is sine R, and that's the reason why the y-axis is sine I, as you see there. Also, again, the whole point of this experiment is, of course, to get the value of n, which is, of course, the refractive index. And you can see now also that n corresponds to the slope on the graph. So you can see that over here, n is now the slope of this line, the line of best fit. And you pick 2 points on that line and you use your slope formula. And of course, when you get slope, that is now equal to n. So that's Snell's law. Now on to the next one. Newton's second law, a bit easier. Again, the maths behind it, F equals ma. F equals ma. If you rearrange that slightly, divide both sides by m. You get 1 over m on this side. The m is now cancelled on this side. So 1 over m times f equals a. And that means that if you compare again to the y equals mx plus c formula, you get y equals mx plus c. Now there's 2 different m's here, not to be confused. So the m corresponds to the m of the formula, which means slope, corresponds to 1 over m, which is the mass. This m in blue is the mass in the formula. And also A, you notice, corresponds to y. The acceleration is now on the y-axis, and the force is now on the x-axis. So that's why you would plot f versus a to get the slope. And the slope is now 1 over mass, as I just said there. So the slope m is 1 over mass. So you measure your slope as usual with your slope formula, and mass is now 1 over slope. So that's Newton's second law. Measuring g by free fall. So we all start off with an equation, so we should be getting used to this now. They all start off with some basic equation. So in this case, it's s equals ut plus a half at squared, distance traveled. So u is the starting velocity. Now, if you drop something, if the ball drops in the experiment by free fall, its starting speed is 0. So that part becomes 0, and now it's just a half at squared. So now our equation is much simpler. It's just simply the height, or s, the height that the ball falls, s, is a half a by t squared, because this term is gone. If you compare that to your equation for a straight line, you notice that the y corresponds to s now. And what I've done here is I've taken the constant parts and put them together, the half a. These parts don't change. T squared is the variable. So that corresponds to x. That varies along the x-axis. S varies along the y-axis. And if you correspond everything, as you can see there, the slope of the graph is now a half of a. Or saying that the other way around, that the slope is a half of a, but a is 2 times the slope. So if you measure the slope of this graph and multiply by 2, you get your acceleration by free fall, which should correspond to roughly 9.8 acceleration due to gravity, g. So beware again, the x-axis of this experiment is t squared, and the y-axis is s. So on to the pendulum. Again, starting off with a formula, the time for the pendulum, periodic time, is t is 2 pi root L over g, where L is the length of the pendulum. Multiply or square both sides, so that becomes t squared on that side. If you square this side, everything inside the bracket here is now squared, so that means 2 squared is 4, pi is pi squared, root L over g squared is just L over g. Yet again, separate out the constant part. So that g is a constant that never changes. So move it over under the 4 pi square, because they're constant as well. Now this whole part here is a constant, and the variable is on its own. And now it corresponds more easily to our format y equals mx plus c yet again. So L corresponds to the x-axis, and t squared, be careful again with the squared, is the y-axis. The y-axis is t squared versus L. Now, as we said, the slope is the constant here always. That's always a constant for the given line. It's also the constant in this formula. So the slope corresponds to 4 pi squared over g. Or reversing that, multiply across by g, divide across by slope, you get g is now 4 pi squared over the slope. And again, you calculate the slope using the usual formula, y2 minus y1 over x2 minus x1. And if you do all that correctly, again, you should get a formula for g, gravity, acceleration due to gravity, roughly 9.8. Boyle's law. Again, pressure is proportional to 1 over volume. That's the same thing as saying pressure is a constant times 1 over volume. And I'll add on the plus 0 here again to emphasize that when it comes to the y equals mx plus c, that the c-intercept is the origin. In other words, it goes through the origin. So that's proportional. P is proportional to 1 over v. And corresponding, again, keep the constant separate the whole time from the variable. The variable is now 1 over v. That corresponds to x. And pressure, P, corresponds to y. So the y-axis is P, the x-axis is 1 over v. And that's that one done. Now we're on to the experiments on sound. Frequency is proportional to root tension. So again, if it's proportional, that means it goes through the origin. there's no C is 0 again. And so if you correspond your equation to the equation y equals mx plus c, you'll see that frequency is a constant times root tension because of the proportionality sign, and root tension now corresponds to x, and the constant corresponds to the slope, and frequency is the y-axis, and c is 0. In other words, there is no y-intercept. It goes straight through the origin. And that's basically that. So just make sure that you plot root t versus f. It's also acceptable in this case to square both of them and plot t versus f squared. On to the next one. So this is frequency versus Lindt. Again, a similar idea. Frequency is proportional to 1 over Lindt. And that means the same thing as saying the frequency equals a constant times 1 over Lindt if they're proportional. And if you correspond to y equals mx plus c, because they're proportional, there's a 0 there, so it goes through the origin again. So c is 0, and you can see now that x corresponds to 1 over L and y corresponds to f. So there's x, 1 over L, and there's y, f. The speed of sound graph. So the speed of sound equation, we always start off with the equation in these. So speed of sound is 4f into Lindt plus 0.3 times the diameter. Again, we rearrange this formula, divide both sides by 4f, and you get c over 4f on this side. 4f is gone on this side. Now what we do, again, separate out things that are variable and constant. So what we do here is we rearrange. We leave the L on its own, and if you leave the L on its own on this side, let me see, this comes across as a minus. So L is equal to, sorry, leave the L there, and this is left where it is as well. The only thing that actually moves is this 0.3d. So that goes across to the other side as a minus, and you get this here. So L is c over 4. Now, the next thing to do, as always, is separate out the constant part from the variable part. So the variable part is 1 over f. You're changing the frequency of the string on the sonometer, and the length changes as a result. So this is the dependent variable. Sorry, this is the independent variable, and L is the dependent variable. And so if you separate out the constant part, the speed of sound c stays constant. 4 is constant, so this part is all constant, and that corresponds to the slope. And the x-axis is now 1 over f, and the y-axis is the Lindt L. So that's what you have here, 1 over f versus L. Now this time it doesn't go through the origin, it's not proportional, there's a minus 0.3d. So that corresponds to c, where it cuts the y-axis. So at this point here, if you take down this reading off your graph, where it cuts the y-axis, and you're going to use that as basically, if you take down that reading, that's c, and then you put that equal to minus 0.3d. So for example, if you're asked to work out d, that's how you'd work out d if you use this point down here. More often than not, though, the whole point of the experiment itself is to measure the speed of sound. And you see, now you can get that by just looking at the slope of the graph corresponding to speed of sound over 4. So slope of the graph is speed of sound over 4 here, or writing it the other way around, the speed of sound is 4 by the slope. So you get your slope the normal way using the slope equation, and then multiply your answer by 4 to get the speed of sound. And the last of the tricky graphs that you can be asked, I suppose, really is Jules Law. Again, starting off with the equation, I squared RT, so the electrical energy, assuming no losses, is transferred to the water, so it's MC delta theta. And if you rearrange that formula, divide both sides by RT, and it disappears over here on this side, and it reappears down here under the line as RT. Now you have I squared is equal to, now you rearrange yet again, keep the variable part separate. So this is the change in temperature, that varies, so does I squared, but everything in here is constant. M, the mass, by C, which is the specific heat capacity, over R, the resistance, and T, time. All of those four things if you think about when you're doing the experiment, they remain constant. So they correspond to the slope in your graph. And yet again, you have a straight line because it now corresponds to y equals mx plus c as long as as long as you plot the change in temperature is the x-axis and I squared is the y-axis. So if you get a straight line in that situation, that proves Jules' law, that and you have now proved that I squared is proportional to change in temperature. And that's the end of the lesson on the physics graphs.